Conformal prediction is one of the most elegant and practical ideas in modern statistics, and it traces back to a single tutorial at ICML 2024. Its title, Distribution-Free Predictive Uncertainty Quantification, presented by Aymeric Diolu-Vu and Margot Zafran in July 2024. This tutorial was led by two researchers, Aymeric Diolu-Vu on the theory and guarantees, and Margot Zafran on the hardest sequential data cases. Together, they cover both the guarantees and the messy regimes where those guarantees are tested.
A single prediction hides its own uncertainty. Conformal prediction promises an interval with a coverage guarantee. Start with a deceptively simple question. Here are 3 datasets, and they all share the same best fit line. In the first, the noise is small and tight. In the second, the noise is large all the way across. In the third, the noise changes as you move along X. Same prediction line, 3 completely different realities. If all you have is the number, you have no idea which world you are in. Weather, medicine, finance, each one needs to know how wide the uncertainty really is. And that is exactly the problem of uncertainty quantification. Over more than 20 years, an elegant tool slowly emerged. In 2005, Vovk and colleagues laid the theoretical foundations. In 2014, Lay and Wasserman helped push it toward the mainstream. Then, in 2019, conformalized quantile regression changed everything. That was the turning point that made conformal prediction explode. A rapid sequence followed: weighted conformal, Jackknife Plus, and adaptive conformal inference. And in 2022 came AgACI, distribution shift, and risk control. Today, conformal prediction is a keynote-level topic. The theory, it turns out, is older than the hype. So, what does this tutorial actually set out to do? First, build the basics carefully, from the mechanics rather than the buzzwords. Second, be honest about both the strengths and the limits. Because what it guarantees and what it does not is exactly where people go wrong. And third, leave you with practical intuition for when these sets actually help. This is not the only resource. There is also Angelopoulos and Bates, Tibshirani's notes, and more. But these 3 goals are why this video exists. Let us state the problem precisely. We have pairs of features x and a value y drawn together. And we want to predict y for a new point xn plus 1. Instead of returning a single number, the point prediction y hat. We return a whole set guaranteed to contain the truth with probability at least 1 minus alpha. So alpha equal to 0.1 means 90% coverage. This interval is what we actually hand back to the user. And remarkably, this holds with no distributional assumption, in finite samples. So where does conformal prediction sit among the schools of uncertainty? There are three big families: classical, Bayesian, and conformal. Classical statistics gives confidence intervals, but it needs assumptions and is often only asymptotic. The Bayesian view is posterior-based and coherent, but it needs a prior. Conformal is different, finite sample, distribution-free, and model-agnostic. That combination is its unique niche. And it is exactly the niche we will spend the rest of this video exploring. We want intervals guaranteed to cover. Split conformal is the simplest recipe, and it comes with the theory that proves it. The simplest, most usable form of conformal prediction is split conformal. We begin with our dataset, where every point is a feature-value pair. The blue points are reserved to train the model. The amber points become a held-out calibration set. And one red test point, whose true value we do not get to see. The training and calibration sets must stay completely separate. Keep that one rule in mind: everything depends on it. On the training points, fit any model you like. Call its prediction mu hat of X. It can be a line, a random forest, a deep network, truly anything. Conformal prediction treats it as a pure black box. On each calibration point, we look at how far the model is off. That gap is the non-conformity score, the absolute residual. It is simply a number for how wrong the model is on data it never trained on. Take every error the model made on the calibration set. Sort them from smallest to largest. Now count up to rank K. The value sitting at that rank is the quantile Q hat. 90% of the errors fall at or below it. Formally, K is the ceiling of 1 minus alpha times n plus 1. That one number, Q hat, is the whole quantile step. For a test point, start at the model's prediction. Widen it by Q hat above and below to form the interval. Reveal the hidden truth, and it lands inside. Do the same for every point, tiling intervals across the data. Count how many truths are covered. About 90%. Exactly the guarantee we asked for. Here is the entire algorithm, one step at a time. Split the data into a training set and a calibration set. Fit any model you like on the training half. Score each calibration point by its absolute residual. Take the 1 minus alpha quantile of those scores. Wrap the prediction in plus or minus Q hat. 5 lines, and that is genuinely the whole method. Conformal needs just one assumption: exchangeability. Picture the dataset as a sequence of points, Z1 through Zn. The joint law of that sequence is all that matters. Reorder them one way and the law is identical. Reorder them another way and it is still identical. Independent, identically distributed data is just a special case. And only the calibration and test points ever need it. The whole proof rests on one fact about ranks. Add the test score to the n calibration scores. There are n plus 1 possible ranks. By exchangeability, every rank is equally likely, exactly 1 over n plus 1. The quantile sits at rank k, so k of the n plus 1 slots are at or below it. So the score is below the quantile with probability k over n plus 1 at least 1 minus alpha. That single fact is the entire engine. We just proved the score lands below q hat at least 1 minus alpha of the time. And being inside the prediction set is exactly the score being below q hat. Watch the score event line up with the membership event. Substitute one into the other and the coverage guarantee falls right out. One line, finite sample with no distributional assumption. Coverage is not just at least 90%, it is also nearly exactly 90%. The two bounds pin it into a razor-thin band of width 1 over n plus 1. Watch the realized coverage slide up and land inside that band. And it asks nothing of the distribution or the model. A good model gives a tight, useful interval. A flat, wrong model just gives a wide one. But both still cover about 90%. Validity is free. Efficiency is what you earn. This single band covers 90% on average. But slide a window across X and measure coverage locally. On the easy side, it overcovers, wasting width. On the hard side, it undercovers, which is risky. Fine on average, wrong locally. Split conformal is valid, but only on average. Now we ask what we'd want for each input, and why it is impossible for free. There is a much stronger guarantee we would love to have. The one we proved is only marginal, true on average. What we really want is conditional coverage at every single X. Here is the band over the data. Slide a magnifier across the feature axis. In this slice, the coverage holds. In this one, it holds too. And here as well. Coverage holding at every X is the gold standard. So, can we get conditional coverage for free? Distribution free and conditional at the same time. Here is one target point and an adversary who controls the distribution. Demand that we cover the truth exactly here. The adversary simply runs its mass off to a far outlier. To keep covering it, the interval is forced open without bound to infinity. Distribution-free conditional coverage is impossible. Think of 3 properties you want all at once: distribution-free, conditional, and informative. The theorem says you can keep only 2. Conformal keeps distribution-free and informative, and gives up conditional, settling for marginal coverage. But could not a clever estimator reach conditional coverage anyway? Here is one that technically does. It just flips a coin. With probability 1 minus alpha, return the whole real line. Otherwise, return the empty set. On average, it covers exactly 1 minus alpha of the time. And it behaves identically at every x, so it is conditionally valid too. Valid, yet completely useless. That is why the theorem is tight. So we relax the goal. Ask for coverage over any large enough region, not at every single point. This is 1 minus alpha, delta conditional validity. But shrink the region you demand it on. And the interval you must return grows wider. No free lunch. More conditional means wider intervals. Between the 2 extremes lies a whole spectrum. At the bottom step, plain marginal coverage. Then a pack, training conditional guarantee. Then coverage within predefined groups. Then local, neighborhood-based coverage. Then approximate conditional coverage. And full conditional sits behind a glass ceiling. Distribution-free, it is impossible. Take the pack rung and make it concrete. The coverage gap shrinks like 1 over the square root of n. Plot that gap, epsilon, against the calibration size. The curve falls steeply, then flattens out. At 1,000 points, the gap is already about 4%. Push to 10,000 and it drops toward 1%. But with a small calibration set, coverage can drift far. That left us a one-size-fits-all band. Now we design a smarter score so the set adapts, tight where easy and wide where hard. A constant width band is the wrong shape for changing noise. It pads the same amount everywhere. So it wastes width where the data is calm and misses where it is noisy. We want a band that breathes, tight here, wide there. The fix is to regress the quantiles, not the mean. At each x, look at the local spread of the data. Fit an upper curve through about the 95th percentile. and a lower curve through the fifth, so the band follows the cloud. Adaptive by construction, but with no finite sample guarantee yet. CQR scores each point by its signed gap to the nearer quantile curve. Here are the two fitted quantile curves on the calibration data. Outside the band, the score is positive. Inside, it is negative. Collect those scores and sort them. Take the 1 minus alpha quantile, Q hat. Then push both curves out by Q hat, restoring coverage. The guarantee is the very same lemma as split conformal. Only the score changes, from the absolute residual to the CQR score. Plug it into the quantile lemma and you get 1 minus alpha coverage. But now the band is adaptive and it still covers about 90% finite sample validity with a width that varies. Validity for free, adaptivity on top. Put split, conformal and CQR on the very same data. Split conformal pads a constant width, far too wide, where the data is calm. CQR lets the band breathe, hugging the noise at every X. Same coverage, but far more informative intervals. Conformal is not just for regression intervals. For classification, the interval becomes a discrete prediction set. We keep every class whose score is below the threshold. Here the set is dog and wolf, size 2. Adaptive prediction sets sort the class probabilities highest first. Then accumulate them until the total crosses the threshold Q hat. Greedily add classes and the prediction set grows until the meter crosses. Confident inputs give a small set. Unsure ones give a large one. But APS can bloat the set with a long, low probability tail. RAPS adds a penalty that grows with the rank of each class. Turn the penalty up and the tail classes drop out of the set. The set shrinks while coverage holds, the size-coverage trade-off. Every method we have seen is the same machine. Split, score, take a quantile, invert to a set, one pipeline. The output is always just a prediction set. The only swappable part is the score you plug in. Snap in a different score and the set changes shape, but the guarantee does not. So, what scores can we choose? Here is one test point and its raw residual. The standard score is just that distance, the absolute residual. The locally weighted score divides it by the local noise. And CQR measures the sign distance past the nearer quantile. Look closer at the locally weighted score. Start from a constant width band. Divide by the local spread, and the band breathes, tight where it is calm, wide where it is noisy. The interval is mu hat plus or minus q hat times rho hat of x. How do we compare methods? By efficiency, the expected width, sweep across x and accumulate the area of the band. Smaller area means a more informative interval. And the oracle is the floor, the smallest band that is still valid. Same data, 3 valid bands. Split conformal is the widest, a constant pad. CQR is tighter, adaptive to the noise. The oracle sits on the floor, the tightest valid band. Validity is free. Efficiency is what you earn. Every method so far wastes data on the split. Now we reuse all of it with full conformal Jackknife Plus and CV Plus. Split conformal forces a hard choice. Spend more data on training and the model gets better. But the calibration quantile turns noisy. Spend more on calibration and the quantile is stable, but the model suffers. A tug of war over the same finite data. Why not just reuse all the data for both? Fit the model, then score it on the very same points. A flexible model can interpolate them perfectly. So every residual collapses to 0. The interval shrinks to a single point, false confidence. Reusing the data breaks the guarantee. So how do we keep all the data and stay valid? 3 approaches: full conformal, Jackknife Plus, and CV Plus. Full conformal avoids splitting entirely. Take a candidate value y to test. Add the pair x, y to the data and refit the model. Score all n+1 points and check where y ranks. Sweep every candidate. The ones that look normal are accepted, the rest rejected. The accepted values form the prediction set with exact coverage. But 1 refit per candidate makes it very expensive. Jackknife Plus keeps the data and drops the split. Fit n models, each leaving exactly 1 point out. Each one gives a leave one out residual. Aggregate those residuals into a single interval. The coverage guarantee is 1 minus 2 alpha. Jackknife Plus still needs n refits, 1 per point. CV Plus uses k folds instead, only k refits. Far cheaper with nearly the same guarantee. Nested conformal unifies them all under one view. Step back and look at the whole map. it opens into an efficiency versus computation plane. Full Conformal, Jackknife Plus, and CV Plus take their places. And Split Conformal anchors the cheap corner. Together they trace a frontier. More compute buys tighter intervals. Pick the point that fits your budget. All of it assumed exchangeability. Now we handle a shifting world by reweighting and by adapting online. Everything so far rested on one assumption: exchangeability. In practice, it breaks in 4 classic ways. Covariate shift. The input distribution moves between train and test. Label shift. The mix of outcomes changes. Arbitrary shift. The whole distribution can change unpredictably. And time series, where today depends on yesterday. Under covariate shift, not all calibration points are equal. Reweight each one by the likelihood ratio of test to train density. Points in high test density regions count more. Take a weighted quantile of the scores. And coverage is restored under the shift. What if you do not know the shift exactly? Coverage then degrades gracefully, not catastrophically. It drops by, at most, the distance between the train and test distributions. Turn the shift up and coverage eases down, but stays bounded. A little shift costs only a little coverage. So far, the data came in a batch. Now it arrives one at a time. At each step, an item rides in on the stream. We emit an interval for it before seeing the answer. Then the truth is revealed, inside or outside. The stream rolls on to the next item. What we want is the long-run coverage to land at 1 minus alpha. Adaptive conformal inference acts like a thermostat. One update rule runs at every step. A miss kicks the dial to widen the next interval. A hit relaxes it back to tighten. The realized coverage self-corrects toward the target. No exchangeability needed. It adapts online. But which learning rate, gamma, should you pick? You do not have to choose. Run several adaptive experts, each with a different gamma. Aggregate their intervals online, favoring the ones that do well. The combination tracks the best expert automatically. Adaptive coverage, with no rate to tune. The method and its theory are built. Now we see it in practice, the full landscape, and where the field is heading. Before we close, 2 case studies put Conformal to work. First, medical imaging, controlling a risk, not just covering a value. Second, Electricity prices, adaptive intervals that ride out a market shock. Conformal is not only about intervals on a number. In medical imaging, the output is a set of pixels, a mask. We want to control a risk, like the false negative rate. Start from a small predicted region. Grow it until the average miss rate drops below the level. Now the risk is controlled, with high probability. And you choose the risk level you can live with. A real case, forecasting electricity prices. Here is the price over time. A fixed width band looks fine in the calm periods. But then a price shock hits. An adaptive band breathes wide through the volatility and narrows again as things settle. Coverage holds through the storm. The interval widens exactly when the uncertainty does. Coverage is a real guarantee, but it is fragile. Data leakage. Train and calibration must stay separate. A tiny calibration set makes the quantile unreliable. A mismatch score gives valid but useless sets. Distribution drift quietly breaks coverage. And do not confuse marginal coverage with conditional. But every hazard has a safeguard. So, which method should you actually use? Is your data exchangeable? Does the noise scale change with the input? Is data scarce, so you cannot waste a split? Follow the answers, and you land on a method, here, CQR. One simple walk picks the right tool. Step back and see the whole conformal landscape. One root idea branches into the families we covered. Split methods, score design, conditional coverage, beyond exchangeability, online, and risk control. All grown from a single guarantee. Where is the field heading? Outlier detection, turning scores into conformal p-values. Selective inference with false discovery rate control. Beyond coverage, controlling decision risk directly. And aggregating prediction sets across many models. The frontier is wide open. We began with a single interval covering the truth. Conformal prediction makes that guarantee simply and powerfully. Marginal is not conditional. Exchangeability is an assumption. Efficiency is earned. But the core idea is remarkably practical. Thank you for watching.